Welcome back. Again, we are dealing with logarithm, which actually also still works on what we refer to as numbers. If you can recall vividly, we have this relationship a equals to b raised to the power of n when we're dealing with indices, where we call a to be the number, where we have b to be the base and n to be the index. Now, this relationship of a, b, and n that we have here has a way of representing them again, but now we call it to be in log form. Now, that simply is to have log of the number, that's a, in base b will always equals to n. Just like we have it here, we can also have it here like this. Now, let me quickly show us what I'm trying to say. If we have 16 as the number to equals to, for example, 4 raised to the power of 2, we are sure that this relationship is correct. 4 raised to the power of 2 equals to 16. In log form, this same expression in log form will be log of the number, which is 16, in base 4, that definitely will equals to 2. That is the relationship between the index form and the log form. There is always a relationship between the index form of a number and the log form of a number, just like we have seen now. So, this relationship holds always. We have some certain things that are guiding our operation under logarithm. Let me quickly give us those laws. Laws of logarithms. Number one, the first one we have is saying when we have log of a in base a plus log of b in base a, the 2 equals to log of a times b in base a. Number 2, when we have log of a in base a minus log of b in base a, the 2 equals to log of a all over b in base a. 3, when we have log of a in base a raised to the power of n, this will equals to n log a in base a. Number 4, if we have log of a in base capital A now, this will equals to 1. And number 5, if we have log of 1 in any base, that will equals to 0. Number 6, when we have log of b in base c, we'll call this change of base. This will be log of b in base a all over log of c in base a. The law number 6 is this: log of b in base c equals to log of b in base a all over log of c in base a. If you look at the first law we have, which says log a in base a plus log a in base a, log b in base a, it says it's equals to log a b all in base a. Do not forget this relationship. If we have this relationship always, that tells me that if I have log of a in base a, there is 1x that this will equals to, which if I want to refer this back to this other side of the relationship, that will equals to, that will give me a equals to a raised to the power of x, and this also will be log b in base a, that will equals to, if that equals to y, that also will give me this relationship where I'm going to have b to equals to a raised to the power of y. What I'm having here, according to this, will give me this. Now, with this understanding, if I'm multiplying A and B, A times B, that is like I'm multiplying A raised to the power of X multiplied by A raised to the power of Y. Is that clear? Beautiful. So if I'm going to say I'm going to take the log on this side, that will give me log of AB in base A. Then it's going to equals to log of, mind you, when we are dealing with log indices, this times this will equals to A raised to the power of X plus Y. Remember? Beautiful. So this now be log of A in A raised to the power of X plus Y. We will soon prove this. That's one of the law we have when we have log of A in base A. AB equals to X plus Y. X plus Y log, I put log A in base A. Log A in base A equals to 1. Log A in base A equals to 1. So I have log of AB in base A to equals to X plus Y multiplied by 1, which is still going to be that same value. So if this is what I'm having, I have log AB in A, that will equals to what I have here, X plus Y. What's my X? What's my Y? My X is log A in base A. So I'll just replace it. Plus Y, log B in base A. That proves the first law for us. Permit me to quickly go to law number 4 that says log of A in base capital A equals to 1. Remember, I want to express this in this form. What would that be? I will have my capital A here equals to A, which is now the base here, raised to the power of 1. You remember this that we did last week when we were dealing with indices? Beautiful. A equals to A raised to the power of 1. So if what we have, any number, is equals to that same number raised to the power of 1. So that confirms this relationship for us, that whenever we have log of any number in the base of that same number, the result equals to 0. And in the same, in like manner also, what happens if we have log of 1 in any base now? What would that be? I say 0. Let's confirm that and see. That will be 1 equals to, according to this relationship, 1 equals to A raised to the power of 0, provided that our A is not equals to 0. You remember we were able to establish this also last week also, that any number which is not equals to 0, whenever it's raised to 0, the answer equals to 1. So log of any, log 1 always, in whichever base it might be, will always equals to 0 according to this relationship. So we have been able to prove this and this. Let me show the second law now. Log A in base A minus log B in base A. The second law says it equals to log A all over B all in base A. Just like what we did earlier while we were dealing with the first law, we're going to have, we know that this relationship will equals to something. Let's say for example X, and we know that this relationship also will equals to something. Let's say for example Y. So with this at the back of our mind, let's now see if we are dividing A by B. What would that be? Because we know from here we're going to have our A to equals to A raised to the power of X, and here also we're going to have our B to equals to A raised to the power of Y. So if we're dividing A by B, this will equals to A raised to the power of X all over a raised to the power of y, which according to our law of indices, this will equals to a raised to the power of x minus y. So if we're taking the log of this side and this side, that will be log of a all over b in base a equals to log of a raised to the power of x minus y in base a of a all over b in base a to equals to x minus y into a bracket log a into a. Like what we just proved now, we have log a in base a to equals to 1. So we have log a all over b to equals to x minus y multiplied by 1, which is log a all over b in base a equals to x minus y. And do not forget, our x and our y equals to something. X equals to log a in base a, log a in base a, minus y equals log b in base a, log b in base a. And that proves the second law for us. Okay, let's consider law number 5. It says log 1 all over x equals to minus log x in base b in base b. From the second law that we just treated, this will equals to log 1 in base b minus log x in base b. And from one of those ones that we have established earlier, we discovered that log 1 irrespective of the base equals to 0. So we have 0 minus log x in base b. That equals to minus log x in base b. That confirms that for us. Let's do the implication of what we have been discussing since. Let's look at some examples. If I'm having log 125 in base 5, and I'm just to simplify this, what do I need to do? Simple. What I'm having here is log 125 in base 5. This is telling me something that if I'm to write it in this form, in the index form, that will be I have 125 as a number equals to 5 raised to the power of something. I want to find what this will be. And from indices, we've been able to establish what that will be. All what we just need to ensure is that the base we're having here will equals to the base we're having here. To make the base equal, here we're going to have 5 raised to the power of 3 to equals to 5 raised to the power of n. Let's work some examples and see what we have been dealing with so far. If we have log 125 in base 5, log 125 in base 5, all what we're looking forward to is to see how we can express this 125 as a number that will be showcasing this base also. And we know that 125 equals to 5 raised to the power of 3. 125 equals to 5 raised to the power of 3. So in that situation, what we're going to have, that will be log 5 raised to the power of 3 in base 5. And from the third law says this will equals to 3 times log 5 in base 5 from the third law, which will be the same thing as saying 3 log 5 in base 5. The fourth law makes us realize that when we have log of any number in that same base, that equals to 1. That tells us that what we have here equals to 3 into bracket of 1, which equals to 3. So log 125 in base 5 equals to 3. For the example, if we have log 27 in base 3, log 27 in base 3, how are we to reflect this base 3 as a result of 27? That will be 3 raised to the power of 3. Here we have log 27 in base 3. We're trying to express 27 as a number having base 3. That would be 3 raised to the power of 3. 27 is 3 raised to the power of 30. So therefore, we're going to have log, instead of writing 27, we're going to put our 3 raised to the power of 30 there in 30. And this will equals to 3 log 3 in base 3 according to law number 3. And according to law number 4, this equals to 1. That is, log a in base a equals to 1. So what we have there will be 3 times 1, which equals to 3. This also equals to 3. Let me give one more there, where we have log of 64 in base 2. Log of 64 in base 2. What we want to look out for is how we're going to express 64 with a number of or with base 2. That is 64, that will equals to 2 raised to the power of 6. 2 raised to the power of 6. So, therefore, this will become log of 64. Instead of writing that 64, we're going to write 2 raised to the power of 6. 2 raised to the power of 6 in base 2. And according to law number 3, this will equals to 6 multiplied by log 2 in base 2. Log 2 in base 2. Then we have it as log 2 in base 2. Mind you, log 2 in base 2 is reflecting our law number 4. And it says that everything we have in this box equals to 1, which gives us 6. So log 64 in base 2 equals to 6. Equals to 6. Another example here, given that log 2 in base 7 equals to alpha, log 3 in base 7 equals to beta, log 5 in base 7 equals to gamma. Please do not be afraid of the alpha, beta, and gamma thing. They are just an expression. The questioner says give expression for log 6 in base 7, log 15 over 2 in base 7, and log 75 in base 7. Now, let's see how we're to deal with this one by one. Number 1, the first one we have there, it says log 6. Log 6 in base 7. And looking at what we're given, we do not have anything 6 there. What we just need to look for now is, from what we're given, what can we actually work together? Can we actually put together that will give us 6? From what we're given. We're given 2, we're given 3, we're given 5. Now, clearly you will see that this is the same thing as saying log what now? Log, instead of 6, we have 2 times 3. Is that correct? In base 7. That's still log 6. Now, according to the first law that we have, it says whenever we have something like this, what do we do? Beautiful. We're going to say this will equals to log 2 in base 7 plus log 3 in base 7. An expression has been given for log 2, an expression has been given for log 3 in base 7. What's the expression for log 2 in base 7? That is alpha. So this equals to alpha plus, what's the expression for log 3 in base 7? That is beta. So the expression we're looking for here for question number 1 is alpha plus beta. For the second one, we have log 15. all over 2 in base 7. If you look carefully at what we have there, we do not have anything 15. But we have things that we can actually express as 15. So in that situation, this will be log in base 7 of 15. That will be 3 times 5 all over 2 that we still have in there. All over 2. So we have this. If we have this, from now, this actually is a combination of law number 1 and law number 2, the multiplication and the division. So therefore it's going to be log of 3 in base 7 plus log of 5 in base 7, then minus log of 2 in base 7. An expression has been given for this, and this. What is log 3? Log 3 is beta plus log 5 is gamma minus log 2, which is alpha. This is the expression for number 2. Now to the third one, number 3. We have log 75 in base 7. Looking carefully, we do not have anything 75 yet. But then we need to think of what we're going to use these things, how we're going to express them in order to get 75. That is where our work lies as students. We need to be able to think out of the box. How do we get 75 from 2, 3, and 5? How? Okay, anybody? Okay, beautiful. That will be log 3 times 5 times 5. Are you checking it with me? 3 times 5, 15. 15 times 5, 75. 75. If you're unable to break it down to this form, you might not be able to solve it. That's the reason why you must be able to think out of the box. So if we have this, what we have now is log 3 times 5 times 5. And the law number 1 still holds for them all. That tells us that we're going to have all in base 7. Log 3 plus log 5 in 7 plus log 5 in 7. So we have this to be beta plus this is gamma plus this is gamma. That is beta plus 2 gamma. That is the expression. Giving us another example where we're just going to be simplifying also this expression log x raised to the power of 2 in base b plus log x raised to the power of 3 in base b minus log x raised to the power of 4 in base b. And we are to simplify this expression. What do we do? We'll be using the combination of law number 1 and number 2 for this expression. This is plus, so when we see plus, when we're adding plus, that will be multiplication, and this is minus. When we're multiplying, that will be, we will need to divide it. That is simple, and it's just log in base b of x squared. Okay, let me x squared times, I'm sorry, I need to distinguish between x squared multiplied by x cubed all over x raised to the power of 4. That is that. So let's see what that would be. X raised to the power of 2 plus 3 all over x raised to the power of 4. That equals to log of b into bracket of x raised to the power of 5 all over x raised to the power of 4. That will give us log in base b of x raised to the power of 5 minus 4, which equals to log in base b of x. Now to the last example for today. We have log a all over b in base k plus log b all over a also in base k. For us to expand this, we'll be using the second law. For us to expand this, we'll be using the second law. And let's see what we're going to do. We have log a in base k minus log b in base k. That is what we have on the left hand side. Plus, let's look at what we have on this side also. That will be log of b in base k minus log of a in base k. Now, let's remove the bracket and see what we'll be left with. We have log a in base k minus log b in base k plus log b in base k minus log a in base k. Collecting the like times, we're going to have log a in base k minus log a in base k minus log b in base k plus log b in base k. This and this, the same expression, and we're subtracting them. That equals to what? 0. Minus this expression, the same, this negative, this positive. That gives us what? Plus 0. That equals to 0. Why logarithm? If you're wondering the reason why you must study it, I need to tell you this, that it is very essential for you to study it because there are some of our physical phenomena that use this concept of logarithm actually to work. The first one that I want to mention is the decibel. Decibel actually what we use to measure the sound around us, and these are always measured using the logarithm notation. Also in chemistry, what we use in measuring the alkalinity or the acidity of a substance, that is what we refer to as the pH scale, is making use of the logarithm notation. Also, I will need to tell you that in our senior secondary mathematics, it is very essential for us to have a very good grasp of logarithm in order for us to be able to do a whole lot of things, a whole lot of manipulation, a whole lot of flexibility when it comes to numbers. For example, in our last class, I mentioned that if there is such a number, a equals to b raised to the power of n, that for any number a and any number b, there exists an n. But to find an n might be very difficult for us, except we make use of this thing we call logarithm. For example, if you have 7 equals to 2 raised to the power of n, and I ask you to find n, you will find it difficult to say. You might even be telling me that such an n will not exist. But in this situation, making use of logarithm, you just need to find the log of 7 on this side, find the log of 2 raised to the power of n on this side, and from there you'll find out that your n will equals to log 7 all over log 2, and that gives you your n. And you'll see the beauty that irrespective of the numbers, you can always relate two numbers together in this very form using the knowledge of logarithm. Thank you. I would love to leave you with this simple challenge. We're finding n here. N equals to log 7 all over log 2. Now, I want you to, over the time before I'll be meeting you next time, find the value of n. And next class, I'll be checking whatsoever you have been able to do. thus far. Thank you.